Good afternoon. Thank you for joining us. Sometimes us professors are accused of being long-winded, so I'm going to stick to my script. Clean energy doesn't exist, without caveats, that is. There is no such thing as a free lunch. Today I'm going to tell you about the sustainable acquisition of minerals and metals. This is necessary for the clean energy transition and is based on my observations over the last 20 years. Over the last 20 years, I've worked on several multi-global national projects. My research seeks cross-disciplinary solutions to support the global clean energy transition aspirations. This makes it possible to find and use critical minerals while reducing carbon footprints and reducing negative impacts on the environment. One such solution is the use of plants to clean up contaminated sites. However, because the process can be so expensive, we can use the plants themselves to generate biofuel and bioenergy to help pay for the program. All right. As the whole world moves towards the use of clean energy to fight climate change, it is important to understand future impacts of such aspirations. This includes the process of acquisition of the so-called critical minerals. For example, in certain places like sub-Saharan Africa, resources are estimated to be about 30% of the world's entire mineral resources. This region could suffer from potential environmental degradation as a result. This picture shows a group of our students that I took to Zambia recently to work on this project. Zambia has a long history of mining where we had traveled with my students. It is located in a region where mining is expected to explode in the coming years. This is because, in the past, mining has primarily focused on traditional minerals like copper, but now the entire region is interested in critical minerals as well. Unfortunately, between 5 and 7 billion tons of mine waste tailings are generated every year. So, with the increased international demand for critical minerals, we can expect additional mine waste to be generated. When a mine reaches the end of its life, it must be closed. If it's not properly closed, there are risks tied to public health and agricultural productivity. This can happen through surface or groundwater contamination, air transmission, uptake by vegetation, and bioaccumulation in food chains. For example, in 2015, a report from the Western Priority estimated the cost of cleaning up old mine sites in the American West to be more than $21 billion. This cost is estimated to be over $1 billion just in Colorado alone. Therefore, new solutions are needed to ensure sustainable and cheap cleanup solutions. A creative approach, therefore, combining plants and plant tissue provides an attractive option. By partnering with local communities and students, our research focuses on identifying local plant species best suited to colonize specific contaminated sites. These plants colonize sites which have been highly polluted with heavy metals without suffering from the negative impacts of the toxicity. Such plants are known as hyperaccumulators. For example, you'd expect to see very little vegetation at some of these contaminated sites. But seeing plants survive and thrive is quite interesting. Why are these particular plants surviving? Why are they thriving? What features make them be able to survive? Because each contaminated site is different, we must use a variety of methods to identify and characterize these sites. So such methods include geophysics, collecting samples using hand augers, and so forth. We can then measure and compare the most efficient hyperaccumulators and the amount and the type of metals that these plants are acquiring in their systems after we harvest the plants. This is important because it can help us also to investigate the capability of different plants to be domesticated at large scales. If these plants can be grown in a greenhouse, in a lab, can they also be grown at the farm scale, and can local communities be trained to grow these hyperaccumulator plants? The domesticated plants could also be used in mining of shallow resources and oil tailings dams, using a process called phytomining. So this picture here shows a special plant called pongamia, which was grown at one of the contaminated sites using soil biomicrobes as an organic fertilizer. Also, we are investigating the potential of value addition to these so-called hyperaccumulator plants. One example would be to generate biofuel and bioenergy from these plants. This can help pay for the cleanup costs that are associated with domesticating these plants at relatively large scales. Such an integrated approach, where we use the plants to absorb the heavy metals and then use the plant tissue later on to generate the bioenergy and biofuel, can be used anywhere in the world. This last picture just shows our students touring a biofuel, bioenergy facility in Zambia. So this field of phytoremediation combined with generation of biofuels and bioenergy is relatively new. So it's an exciting opportunity for students, communities, different governments, and others to join together, partner with us here at Colorado School of Mines. There's potential that if this is successful, this can be a huge game changer in the whole world. Thank you.